In the last two lectures, I have introduced the concept of likelihood ratio tests. We consider derivation of the likelihood ratio test for some one sample problems, and especially for the parameters of normal distribution when we have a sample from one normal distribution. Then later on I introduced two normal populations, and we had independent random samples from both of them. We considered the test for comparing the means, and in that I had given the test for mu 1 less than or equal to mu 2, the null hypothesis. Now, today I will firstly derive the test when we are having the null hypothesis as equality and the alternative hypothesis as the inequality. So, here let us consider. So, let me reintroduce the model here. Let x 1 x 2 x m be a random sample from normal mu 1 sigma square distribution, and y is equal to y 1 y 2 y n is a random sample from normal mu 2 sigma square, and x and y are also independently taken. This is the model I had introduced yesterday. Yesterday we had considered the hypothesis mu 1 less than or equal to mu 2. Now, today I will consider mu 1 less than or mu 1 is equal to mu 2 against mu 1 not equal to mu 2. Another important point to notice here is that in the likelihood ratio test, the alternative hypothesis does not play a role, whereas in the Neyman-Pearson theory, the alternative hypothesis has to be specified in order to discuss the power, because we are talking about the most powerful, uniformly most powerful, or the UMP unbiased tests. So, all the time power is a consideration. In the likelihood ratio test, we are only looking at the null hypothesis parameter set and the full parameter set. Of course, by elimination what is happening is that when we are taking the full parameter space, the complementary space of the null hypothesis space is the alternative hypothesis parameter space. Therefore, indirectly it is playing a role, and you have already seen yesterday that the tests which we are deriving using the likelihood ratio method they are actually the same as the UMP unbiased tests for the parameters of normal distributions. Now, we consider this particular hypothesis. Now, as before, let me write down the likelihood function here. So, mu 1 mu 2 sigma square, these are the parameters here, and so the likelihood function L theta x y, that is equal to 1 by sigma root 2 pi to the power m plus n e to the power minus 1 by 2 sigma square sigma x I minus mu 1 square minus 1 by 2 sigma square sigma y j minus mu 2 whole square. So, we have already seen that over the full parameter space omega, that is mu 1 mu 2 sigma square, where mu 1 mu 2 are real and sigma square is positive. Over this, the maximization of L gives mu 1 omega head is equal to x bar, mu 2 omega head is equal to y bar, and and sigma omega head square, that is equal to 1 by m plus n sigma x I minus x bar square plus sigma y j minus y bar whole square. So, if we use this, L head omega, that is turning out to be 1 by 2 pi sigma omega head square to the power m plus n by 2 e to the power minus m plus n by 2. Now, we consider maximization of L over omega h, that is mu 1 mu 2 sigma square, mu 1 is equal to mu 2 and sigma square is positive. So, now let us write down the likelihood function in the modified form, because here now mu 1 is equal to mu 2. So, L is now 1 by 2 pi sigma square to the power m plus n by 2 e to the power minus 1 by 2 sigma square sigma x I minus mu square plus sigma y j minus mu square. That means, I have taken here mu 1 is equal to mu 2 is equal to mu. Okay. So, log of L, that is equal to minus m plus n by 2 log of 2 pi minus of m plus n by 2 log of sigma square minus 1 by 2 sigma square sigma of x I minus mu square plus sigma of y j minus mu square. So, let us consider the maximization of this with respect to mu and sigma square. So, derivative with respect to mu, that will give me minus 1 by 2 sigma square. Then here if I differentiate this and this term, I will get minus 2. So, this will become plus and I will get n x bar minus mu plus sorry, this is m x bar minus mu plus n y bar minus mu, that we can say m x bar plus n y bar minus m plus n mu, and this 1 by sigma square will be outside. So, easily you can see this is greater than 0 for mu less than m x bar plus n y bar divided by m plus n, and less than 0 for mu greater than m x bar plus n y bar divided by m plus n. So, L is maximized with respect to mu when mu is, so we call it mu head omega h is equal to m x bar plus n y bar divided by m plus n. So, this is the maximization of L with respect to mu when the null hypothesis mu 1 is equal to mu 2 is true. Now, based on this I can consider the maximization with respect to sigma square. For maximization with respect to sigma square, we consider del L by del sigma square, that is equal to minus m plus n by 2 sigma square plus 1 by 2 sigma to the power 4 sigma x I minus mu square plus sigma y j minus mu square. This you can follow from looking at this term here, that if I have differentiated this term with respect to sigma square. So, this term gives me minus m plus n by 2 sigma square, and this term gives me 1 by 2 sigma to the power 4 into this term. So, once again we can write down this as m plus n by sigma to the power 4, 1 by m plus n sigma x I minus mu square plus sigma y j minus mu square minus sigma square. So, naturally you can see this is greater than 0 for sigma square less than 1 by m plus n sigma x I minus mu square plus sigma y j minus mu square, and it is less than 0 for sigma square greater than this value. So, maximization with respect to sigma square occurs at this quantity, that is 1 by m plus n sigma x I minus mu square plus sigma y j minus mu square. So, we can say that sigma omega h head square, that is equal to 1 by m plus n sigma x I minus mu omega h head square plus sigma y j minus mu head omega h square. Now, mu head omega h that we evaluated just now, that is equal to m x bar plus n y bar divided by m plus n. So, this value we substitute here. We can simplify sigma omega h head square as 1 by m plus n sigma x I minus m x bar divided by n y bar divided by m plus n y j minus m x bar plus n y bar divided by m plus n square. In this first term I add and subtract x bar here, and in the second one I add and subtract y bar. So, this becomes 1 by m plus n sigma x I minus x bar plus x bar minus m x bar plus n y bar divided by m plus n y j minus y bar plus y bar minus m x bar plus n y bar divided by m plus n square. So, that is equal to 1 by m plus n, and this term now I expand. So, I will get sigma x I minus x bar square plus, now this second term if I simplify, I get m x bar plus n x bar minus m x bar minus n y bar divided by m plus n. So, m x bar gets cancelled out, and I get n divided by m plus n x bar minus y bar, and this will be squared. So, I get n is square by m plus n square x bar minus y bar square. Then there is a cross product term twice sigma x I minus x bar into x bar minus, that is the same term, n by m plus n x bar minus y bar. Now, this term is nothing but 0, because sigma x I minus x bar is 0. Similarly, I expand the second term. If I expand the second term, I will get sigma y j minus y bar square plus, now if I look at this second term, I can write m y bar plus n y bar minus m x bar minus n y bar. So, this gets cancelled out. So, this becomes m square divided by m plus n whole square y bar minus x bar whole square, and once again this cross product term sigma y j minus y bar into m by m plus n x bar minus y bar gets cancelled out. Now, the term that is remaining, I can actually simplify this. This I can write as 1 by m plus n sigma x I minus x bar whole square plus sigma y j minus y bar whole square plus m n by m plus n x bar minus y bar whole square. That is the term that I will be getting after simplification of this term here. So, if I substitute this value, so this is my sigma omega h head square. So, in the likelihood function, if I substitute this value, that is 1 by sigma omega h head square, and here I substitute this value. So, here this is obtained after substituting mu 1 mu 2 is equal to mu. I will get, so we will get L head omega h as equal to 1 by 2 pi sigma omega h head square to the power m plus n by 2 e to the power minus m plus n by 2. Now, we have obtained the maximization over the null hypothesis parameter set. We have also derived L head omega, that is the maximization over the full parameter set. So, the likelihood ratio that is lambda x y here, that is L head omega h by L head omega, that will become sigma omega head square divided by sigma omega h head square to the power m plus n by 2. So, likelihood ratio test is reject h if lambda x y is less than c. Now, that will be equivalent to that sigma omega head square divided by sigma omega h head square is less than some c 1, and then we can substitute these values here. Sigma omega head square was obtained as it was 1 by m plus n sigma x I minus x bar whole square plus sigma y j minus y bar whole square. So, this term is sigma x I minus x bar square plus sigma y j minus y bar square divided by sigma omega h head. This we calculated just now. So, that is again equal to sigma x I minus x bar whole square plus sigma y j minus y bar whole square plus m n by m plus n x bar minus y bar square. I am saying it is less than c 1. So, I can take reciprocal of this inequality, taking reciprocal and further simplifying, we can write the rejection region as so, when I take reciprocal, this comes in the numerator and I divide by this full term, I get 1, then I take it to the other side. So, I get the term as m n by m plus n x bar minus y bar square divided by SP square greater than some C 2, where SP square is the pooled sample variance, that is sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n minus 2. So, if I take the square root, I get square root m n by m plus n modulus of x bar minus y bar divided by S p greater than say C 3. Now, we would require, let me give this term as t, probability of t greater than C 3 when mu 1 is equal to mu 2, it should be equal to alpha. Now, in yesterday's lecture, I have given the distribution of this, that is so this is modulus t, this term is t, that is root m n by m plus n modulus of x bar minus y bar S p. So, this follows t distribution on m plus n minus 2 degrees of freedom when mu 1 is equal to mu 2. So, C 3 we can take to be t m plus n minus 2 alpha by 2, that is the upper 100 alpha by 2 percent point. So, this is t m plus n minus 2 alpha by 2 point. This probability is alpha by 2 if this is the curve of t distribution on m plus n minus 2 degrees of freedom, that is the density function of this. So, you can see here likelihood ratio test is reject H if modulus of t is greater than or equal to t m plus n minus 2 alpha by 2, and this is same as the UMP unbiased test for this problem. So, once again this likelihood ratio procedure leads to excellent tests, or you can say optimal tests, as we have derived using the Neyman Pearson theory. Let me again repeat the model. We are considering the two sample problem. I had taken variances to be common. Now, in general situations, we do not know whether the variances will be common or not. So, in order to test about the comparison of the means, we firstly need to check whether the variances are the same or not. So, let us consider the testing for the variances. In two sample problems, for testing about means, we have assumed the equality of variances, that is sigma 1 square is equal to sigma 2 square. However, in practice we do not know this. So, it is advisable to carry out a test for equality of variances. So, I will provide this here. We have the model, that is x 1, x 2, x m, that is x is a random sample from normal mu 1 sigma 1 square, and y is equal to y 1 y 2 y n is a random sample from normal mu 2 sigma 2 square. For comparison of the variances, I consider the hypothesis of the nature, say h 1 sigma 2 square by sigma 1 square less than or equal to some number, say tau naught, tau let us say, and h 2 sigma 2 square by k 2 k 1, that is the alternative hypothesis, sigma 2 square by sigma 1 square is greater than tau, say. Let me call this as tau and this as tau naught value, this is tau. So, we want to check whether tau is less than or equal to tau naught and or tau is greater than tau naught. That means, my likelihood ratio, when I am considering, I will represent in the terms of this ratio tau. Okay. So, consider the likelihood function. Now, note here my parameter is now 4 dimensional parameter is there, mu 1, mu 2, sigma 1 square, sigma 2 square. The null hypothesis parameter set is this mu i's are real and sigma I square is positive for I is equal to 1, 2. And in the null hypothesis parameter set, we are having the restriction that sigma 2 square is less than or equal to tau naught sigma 1 square, and of course, both are positive. So, this additional restriction has come here. So, the likelihood function now L theta x y, that is equal to 1 by 2 pi sigma 1 square to the power m by 2, 1 by 2 pi sigma 2 square to the power n by 2 e to the power minus sigma x I minus mu 1 square by 2 sigma 1 square minus sigma y j minus mu 2 square by 2 sigma 2 square. So, we consider the log likelihood, that is equal to minus m plus n by 2 log of 2 pi minus m by 2 log of sigma 1 square minus n by 2 log of sigma 2 square minus 1 by 2 sigma 1 square sigma x I minus mu 1 square minus 1 by sigma 2 square sigma y j minus mu 2 square. So, this is a full setup with 4 parameters in the 2 normal populations and they are independent. Therefore, the solution is straightforward here, that is, if I consider del L by del mu 1, that will give me m x bar minus mu 1 by sigma 1 square less than 0 for mu 1 greater than x bar greater than 0 for mu 1 less than x bar. So, mu 1 omega head, that will be equal to x bar. Similarly, if I consider say del L by del mu 2, then that will be n y bar minus mu 2 divided by sigma 2 square. Once again, it is less than 0 for mu 2 greater than y bar, less than, and it is greater than 0 for mu 2 less than y bar. So, mu 2 head omega, that is equal to y bar. Let us also consider maximization with respect to sigma 1 square and sigma 2 square. So, let us look at this term del L by del sigma 1 square, that is equal to minus m by 2 sigma 1 square plus 1 by 2 sigma 1 to the power 4 sigma x I minus mu 1 square. that is equal to m by 2 sigma 1 to the power 4 1 by m sigma x I minus mu 1 square minus sigma 1 square. So, this is greater than 0 for sigma 1 square less than 1 by m sigma x I minus mu 1 square. It is less than 0 for sigma 1 square greater than 1 by m sigma x I minus mu 1 square. So, the maximization with respect to sigma 1 square is then occurring at 1 by m sigma x I minus mu 1 square. Now, mu 1 is maximized at x bar. So, it is 1 by m sigma x I minus x bar whole square. Now, similarly, if I look at the maximization with respect to sigma 2 square, that will become 1 by n sigma y j minus y bar square. Now, these values I substitute in likelihood function. In this likelihood function, if I substitute the maximizing values, I get, so L head omega, that becomes equal to 1 by 2 pi to the power m plus n by 2 sigma 1 omega head square to the power m by 2 sigma 2 omega head square to the power n by 2 e to the power minus m plus n by 2. Under omega h, now let us consider. Under omega h, we are having, now if you look at the maximization with respect to mu 1 and mu 2, there is no dependence on sigma 1 square and sigma 2 square. So, it will not change. Since maximization of L with respect to mu 1 and mu 2 does not depend on sigma 1 square and sigma 2 square, we get L head mu 1 head omega h as x bar, mu 2 omega h head as y bar. However, if I consider for sigma 1 square and sigma 2 square, then here we are having the region sigma 2 square is less than or equal to tau naught sigma 1 square in the alternative hypothesis set, that is sigma 2 square less than or equal to tau naught sigma 1 square. So, this will play a role here. So, for maximization with respect to sigma 1 square and sigma 2 square, we first say fix sigma 1 square say. Okay. Then we are saying sigma 2 head square is less than or equal to. So, if I consider the derivative of the likelihood function with respect to sigma 2 square, I get minus n by 2 sigma 1 sigma 2 square plus 1 by 2 sigma 2 to the power 4 sigma y j minus mu 2 square, that I can write as n by 2 sigma 2 to the power 4 1 by n sigma y j minus mu 2 minus sigma 2 square. So, this is less than 0, it is greater than 0 for sigma 2 square less than 1 by n sigma y j minus mu 2 square, and it is less than 0 for sigma 2 square greater than this number. So, the behavior of the likelihood function with respect to sigma 2 square, that means, if I consider the plotting of the likelihood function with respect to sigma 2 square, then at the point 1 by n sigma y j minus mu 2 square. This is the maximization point. Now, if this quantity 1 by n sigma y j minus this is occurring at y bar square, because I have substituted mu 2 head is equal to y bar. So, here I can put mu 2 as 1 by n sigma y j minus y bar square, as mu 2 head omega h, that is equal to y bar. Okay. So, if 1 by n sigma y j minus y bar square is less than sigma 1 square tau naught, then sigma 2 head square, that is equal to 1 by n sigma y j minus y bar square. Otherwise, suppose tau naught sigma 1 square is here. If that is happening, then sigma 2 head square, this maximization is then occurring at this point, that is equal to sigma 1 square tau naught. So, we are saying sigma 2 head square is equal to actually minimum of tau naught sigma 1 square and 1 by n sigma y j minus y bar square. So, when sigma 2 omega head square, that is equal to 1 by n sigma y j minus y bar square, I will get L head omega and L head omega h same, and so we always accept h 1, because the likelihood ratio is supposed to be between 0 and 1. So, if it is equal to 1, we always accept h. Now, the other case, when sigma 2 head square is equal to tau naught sigma 1 square. In that case, with respect to sigma 1 square, when I consider the likelihood function, let us look at the term once again. Let me look at this term L, small l. So, small l theta, that is equal to, now this will become, so these terms will be there, minus m by 2 log of sigma 1 square minus n by 2 log of tau naught sigma 1 square minus 1 by 2 sigma 1 square sigma x I minus mu 1 square plus 1 by tau naught sigma y j minus mu 2 square. Now, we have already got the maximizing values of this. So, I will put it here x bar here. So, this term, then I get minus m by 2 log of sigma 1 square minus n by 2 log of tau naught sigma 1 square minus 1 by 2 sigma 1 square sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar whole square. Okay. That means, the maximization problem with respect to sigma 1 square, now it has been reduced to maximization of this term. So, let us consider that now. So, now del L by del sigma 1 square, that will give me let us look at this thing. So, minus m by 2 sigma 1 square minus n by 2 sigma 1 square, and this term will not play a role, plus 1 by 2 sigma 1 to the power 4 sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square. So, that I can write as minus m plus n by twice sigma 1 to the power 4 1 by m plus n sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square minus sigma 1 square. So, if we carry out the analysis as we have been doing, so analyzing as before, we get here sigma 1 omega h head square, that is equal to 1 by m plus n sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square, and sigma 2 omega h head square, that is tau naught times this. So, it becomes tau naught divided by m plus n, and the same term here x I minus x bar square plus 1 by tau naught sigma y j minus y bar square. So, these values then I substitute in the likelihood function to get L head omega h as 1 by 2 pi to the power m plus n by 2, and then I will be getting. So, if you look at the original form of the likelihood function here, you see here sigma 2 square I am saying sigma 1 square tau naught. So, this term and this term will get combined and tau naught's power will come here. So, I will get tau naught to the power n by 2, and then these two will get combined. So, I will get sigma 1 omega h head square to the power m plus n by 2 in the denominator. And then in the exponent part, here also what is happening, sigma 2 square is sigma 1 square tau naught. So, this term I get outside, then I get sigma x I minus x bar whole square plus 1 by tau naught sigma y j minus y bar whole square, and 1 by tau naught is coming. So, this term will get simply cancelled out, and I will get e to the power minus m plus n by 2. So, let us look at the expressions that we derived. In the page 11, I have written the expression for this value here on page 9. Yeah, L head omega. So, you look at this L head omega is this. So, this coefficient is common in L head omega h and L head omega, and here I am getting sigma 1 omega head square and sigma 2 head omega square, and here it is same term sigma 1 head omega h square to the power m plus n by 2. This e to the power minus m plus n by 2 will also get cancelled out when I take the ratio. So, the likelihood ratio test then will give me. So, the likelihood ratio test is reject h 1 if lambda x y, that is equal to L head omega h by L head omega less than c. This is equivalent to sigma 1 head omega square to the power m by 2 sigma 2 omega head square to the power n by 2 divided by sigma 1 head omega square to the power m plus n by 2 and tau naught to the power n by 2 less than say c. I have cancelled out the constant terms from here. Once again, this does not play any role here, and these terms then I simplify. What I do firstly, because in the sigma 1 omega head h, this is h here, in this term I am getting both is sum of squares. Here only sum of squares of the first term is coming. So, this is equivalent to, I can say, sigma x I minus x bar square to the power say m by 2 sigma y j minus y bar square to the power say n by 2 divided by sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square to the power m plus n by 2 greater than less than say c. Some coefficient will get cancelled out, because for example, 1 by m was here, 1 by n is here. So, let me call it C 1 here. So, this is then equivalent to, I take the reciprocal, I can express it as sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square to the power m plus n by 2 divided by sigma x I minus x bar square to the power m by 2 sigma y j minus y bar square to the power n by 2 greater than say C 2. Now, let me define u is equal to sigma y j minus y bar square divided by sigma x I minus x bar square. So, in terms of this ratio, this condition can be written as, in terms of u, the rejection region can be written as 1 plus u by tau naught to the power say m by 2, 1 by u to the plus 1 by tau naught to the power n by 2 greater than say C 2. Now, let us consider this term as say g of u. Then let us look at the g prime u, that is equal to m by 2 1 plus u by tau naught to the power m by 2 minus 1 into 1 by tau naught into 1 by u plus 1 by tau naught to the power n by 2 plus n by 2 1 plus u by tau naught to the power m by 2 1 by u plus 1 by tau naught to the power n by 2 minus 1 minus 1 by u square. So, this is greater than or equal to 0 if and only if. So, this will require certain simplification. I can take common 1 plus u by tau naught to the power m by 2 minus 1 and 1 by u plus 1 by tau naught to the power n by 2 minus 1. If I take this common and adjust the terms, the condition is reducing to simply m by tau naught into 1 by u plus 1 by tau naught greater than or equal to n by u square 1 plus u by tau naught, which is equivalent to m by tau naught minus n by u greater than or equal to 0, or u is greater than or equal to n by m tau naught. So, this function is actually having increasing nature, this g u function. So, g u is increasing if u is greater than or equal to n by m tau naught, and it is decreasing if u is less than n by m tau naught. But what is tau naught? That is sigma y j minus y bar whole square divided by sigma x I minus x bar whole square. So, the condition lambda x y less than c, this is then equivalent to u greater than or equal to n by m tau naught, or we can write it in the terms of sigma y j minus y bar square divided by sigma 2 square by n minus 1 divided by sigma x I minus x bar whole square divided by sigma 1 square m minus 1 that is greater than say some C 3. Now, when I consider the probability of this region for sigma 2 square by sigma 1 square less than or equal to tau naught, then supremum of this is attained at. So, you look at the distribution of this. This has sigma y j minus y bar whole square by sigma 2 square n minus 1 divided by sigma x I minus x bar whole square by sigma 1 square m minus 1. This follows f distribution on n minus 1 m minus 1 degrees of freedom. So, now what we are saying is f n minus 1 m minus 1 greater than C 3. So, what we look at this, that I adjust this term and I get here the maximum is attained at sigma 2 square by sigma 1 square is equal to tau naught. So, C 3 point then we take as f of n minus 1 m minus 1 alpha. So, the test is the likelihood ratio test rejects H naught H 1 if sigma y j minus y bar square divided by n minus 1 divided by sigma x I minus x bar whole square divided by m minus 1 is greater than f n minus 1 m minus 1 alpha. Here tau naught will be coming sigma 2 square by sigma 1 square, 1 by tau naught will be coming here, because here I should have sigma 2 square by sigma 1 square, that is equal to tau naught. So, same as the UMP unbiased test that I derived that day. I will carry out the analysis for the equality test also, that is when we want to test that sigma 2 square by sigma 1 square is equal to delta naught or tau naught or against not equal to, and there of course, I can take the case where tau naught is equal to 1. So, I will be discussing this case in the following lecture. Moreover, there is another important problem in testing of hypothesis. I have discussed two normal populations. Now, in place of two normal population, we may have k normal population, where k can be 3, 4 and so on. And we may again like to test about the equality of means. So, the UMP unbiasedness theory does not work there, because we cannot write the mu 1 is equal to mu 2 etcetera in a form which can be working as a multi-parameter exponential family. However, for these situations a likelihood ratio test can be derived. So, this is the problem of testing homogeneity of means in a one way analysis of variance model. So, in the next lecture I will be discussing that also.